at this point, what you should be able to see is my desktop with our worksheet number 4 on it. So there's the problem that we did before with the roller coaster and folks going down the hill on the roller coaster. I'm grab a couple pens, my calculator. Okay, so we're going to go ahead and move over to problem number 2 because that's one we haven't worked on together. So here we've got a person who has a box sitting on a line of rollers. This would be like at the grocery store. I forget which store had these a while back. But here's a person who's pushing a box on a line of rollers on a roller track. We're going to assume that friction is small enough to be ignored. We've got a push from our worker at 25 newtons directed down and to the right at an angle of 20 degrees as shown in the picture. Our first task is to draw a force diagram on the block. Well, because this is a horizontal surface, we're going to go with horizontal axes for this problem. So we're not going to have anything that's on a slope, but we are going to have a push that's at an angle. So we are going to have something that's not on those axes. What our block is experiencing is going to be gravity. So I'm going to draw that in there. And I know how big that ought to be because we've got a 7 kilogram container. So this is going to be minus 70 newtons of force. We've got normal force upward. And then we've got a push that's down and to the right. So if we take a look at this, there's where the push is going to go. And we always want to make sure that we draw our vectors in the direction that they're being pushed. And so rather than pushing up here, we're going to have our arrow start in the center of our force diagram where our mass would be, and then downward. And so this is going to be our push down. Because of geometry, if we know this angle, that's going to be congruent to the angle directly across from it. So we know that this is our 20-degree angle. So when we think about this, we're going to need to ultimately be doing is also considering a horizontal push here. So this is going to be the force of the push in the horizontal direction or the x direction. There's also going to be a force in the y direction. And the way that we come up with those, just like we have in the past, is if we imagine that there's a rectangle with our vector as the diagonal, and then the sides that lay on the axes are going to be the vertical and horizontal components of that push. So there's our diagram so far. Oh, we also know that this push is 25 newtons of force. There we go. Part B says determine the horizontal component of the worker's push. This is asking us to solve for the horizontal component, which is going to be this FPX. And in order to do that, we're going to need to use our triangle where, hold on, let me focus this again, make sure it's clear. We're going to use that triangle where we've got our 25 newtons from our push. And we're going to solve for FPX, this guy up here. And we know that this angle in between those two legs is 20 degrees. So since it's an adjacent leg, we're going to use cosine to solve for that. So we would say that the cosine of 20 degrees is equal to the length of the adjacent leg, FPX, over the length of the hypotenuse of our triangle, which is going to be force push, or that 25 newtons. So if we multiply both sides by 25 newtons, we get 25 newtons times the cosine of 20 degrees, and we find that that's equal to 25 times cosine 20, whoops, 20. I got 23.5 newtons. So that's a pretty shallow force. So most of our force is going to end up being horizontal. I can label this up here too, 23.5 newtons. Next, it says write a net force equation for the horizontal forces on the block, the ones that are side to side. So we know that one of our horizontal forces is FPX. We're also told that friction is small enough to be ignored. So we're not going to include anything going the opposite direction because we're told to ignore it. So our net force in the horizontal direction is just going to be FPX. We also know that that's going to be equal to the mass times the acceleration of those blocks. That's just our net force equation. Next, determine the acceleration of the block. Well, this is going to be pretty straightforward because we can do that just by focusing on part of our net force equation. So we know that Fpx is equal to the mass times the acceleration, so we can rewrite that. And to solve for acceleration, we need to divide both sides by the mass. So we're going to end up with our force of the push in the horizontal direction divided by the mass of our box. So we're going to have 23.5 newtons divided by our mass, which was 7 kilograms. So I still have the number that I rounded from in my calculator. I'm just going to leave it there. Do divided by 7 kilograms, and I got 3.36 meters per second squared, because that's what newtons divided by kilograms gives me in units. Next, it says determine the normal force on the block. This one is probably the trickiest one, because in order to do that, what we have to understand is that normal force is going to be equal in magnitude to both the downward component of the push and gravity. So we need to know both of those. So to figure out our normal force, what we need to keep in mind is that our net force is going to be equal to normal force plus the vertical component of the push plus gravity. Right? And if those things are balanced, we would say that our net force is 0. So we would say 0 is equal to normal force plus this guy, which we don't know yet, plus our force due to gravity, which is minus 70 newtons. So in order to figure out, to solve for FPY, what we're going to use is our equation, or our triangle that we solved for earlier, where we've got 25 newtons this direction, we've got 20 degrees that way, and we want to solve for the opposite side this time. And so if we want to solve for the opposite side, we're going to be using sine. So now the sine of 20 degrees is equal to Fpy divided by 25 newtons. Fpy equals 25 newtons times the sine of 20 degrees. And so that value would be 25 times. So I got 8.55 newtons there. And that's going to be downward. So when I put it in here, I'm going to minus 8.55 newtons. Okay. So now what I'm going to do is take my normal force and I'm going to add each of these to the opposite side of the equation. So I'm going to have 8.55 newtons plus 70 newtons. Oops, sorry. Plus 70 newtons. Equals 78.55 newtons. So that's what my normal force ought to be. So it's larger than gravity, because if this person starts pushing on it, in order for that track not to collapse, normal force has to push back up on the box so that it doesn't fall through. You guys have any questions about number 2? All right. We move to number 3. Okay, so for number 3, we've got a box being pulled by 400 newtons of force at an angle of 30 degrees to the horizontal. The force of kinetic friction is 75. So we know that we're going to have a force along this rope that's 400 newtons. And we've also got kinetic friction that's moving opposite the direction, or sorry, that's pointed opposite the direction of the motion of the box. So our kinetic friction, so I'm going to write Fk, is equal to 75 newtons. First thing we need to do is draw a quantitative force diagram for the box. So I'm going to put my dot there. I'm going to have horizontal and vertical axes with no tilt because there's no slope there that I need to worry about. My angle is that a rope is being pulled to the side, but that's okay. That doesn't mean we have to rotate everything. In order to make a quantitative force diagram, I'm going to put my forces on here. I already know that I've got kinetic friction, that's 75 newtons. I've got gravity downward. And for my box, that's 70 kilograms. It's going to be minus 700 newtons. We're going to have normal force upward. We don't know how big that is because whenever we have more than one component that's pulling up or down, we're going to have to do some solving to figure that out. We've also got something that's at an angle of 30 degrees that's off to the side. This one's actually quite large. I should have drawn it a lot longer, but we'll just roll with it. Here we go. All right, this asks us to be quantitative. And so to figure out some of this stuff, we're going to need to figure out the component forces that are going on. So we need to know what this component is. This is the force of my pull in the horizontal direction. So I labeled it FPX. If I imagine that that's a rectangle, my FPY is going to be over here. So that's my vertical component of the pull. So when this person is pulling on the box with the rope, they're pulling both up and to the side. To figure out what those should be, should look something like, with this FPX, we're going to use the cosine of that value. So our FPX is going to be 400 newtons times the cosine of 30, which is going to give us I got 346 newtons for that. And my FPY value is going to be a similar setup, except for now I'm going to be looking at the opposite side of that triangle for 30 degrees. So that's going to give me I'm going to need to use my sine relationship for that. So 400 newtons times the sine of 30 degrees, which is going to be 200 newtons. So those are my values that should go with those forces. Next, it says determine the acceleration of the box. I'm assuming that they're talking about the acceleration in the horizontal direction because my box isn't going to all of a sudden start lifting up off the floor. So in order to figure that out, I need to use a net force equation. So my net force is going to be the sum of the horizontal forces, which is going to be FPX plus F friction kinetic. And that's going to equal the mass times the acceleration of the box. And what we're solving for here is acceleration. So in order to do that, what I'm going to do is focus on my two forces and Newton's second law. I'm going to divide both sides of this equation by mass. So acceleration is going to be the force of the pull in the horizontal direction plus the force of friction divided by mass. Keep in mind, one of these is going to be negative and one's going to be positive. So I'm going to use the direction to the left as my negative direction. So minus 346 newtons plus 75 newtons divided by the mass of the box, which is 70 kilograms. That's going to give me plus 75 divided by 70. I got minus 3.87 meters per second. And the negative there is just telling me which direction it's going because I set up my problem so that the left was negative and the right was positive. My value is going to be in the negative direction. If you set yours up so that the direction that the object was being pulled was positive and friction was negative, then you would get the same number but an opposite sign, and that's okay, as long as you're clear about that when you're doing your work. Okay, I'm going to give you guys a second in case anybody wants to ask any questions. All right, number 4 is kind of interesting because it's a little bit tricky. In order to figure this out, we have to actually picture these a different way. This is Atwood's machine. Before we talked about a modified Atwood's machine where one of the blocks was sitting up on a ledge. This is Atwood's machine where you have two masses that are hanging on either side of a pulley. We're told that the pulley is frictionless. and we're given the mass of both blocks. And so in order to do this problem, I'm first going to note some of the things that are written in the problem here. So here for A, I'm going to write that that is a 5 kilogram mass. B is a 2 kilogram mass. So I'm going to record that. And then we're asked to determine the acceleration of the system when the blocks are released. Well, we know when we let go of these blocks that the only forces acting on them, if there's no friction, is going to be a force from gravity. So there's going to be a force of gravity on A. There's going to be a force due to gravity, G, on B. So we've got those two forces, and they're both downward, which makes it kind of tricky to think about. But what we're going to do is take these two blocks and imagine that because the forces are going downward, but they're attached by a string, it really means that if we pull downward on B, that we're pulling upward on A. And so these two forces, even though both of them are downward, are both acting in opposite directions. And so just like we did with the modified Atwood's machine, we're going to reimagine the way that this looks. So we're going to kind of move these blocks. Instead of hanging over a pulley, we're going to just grab them and straighten it out so that we've got block A on that side, and then we've got block B on the other side. So there's A and B, and their forces, instead of both of them pulling down, they're pulling away from each other. So we're going to have our force due to gravity of B going to the right, and our force due to gravity on A going to the left. We also can say what those forces actually are, right? Because this is just going to be the mass times acceleration due to gravity. So for A, we're going to multiply our 5 times 10. This one's going to have a magnitude of 50 newtons, while B on the other side has a magnitude of 20 newtons. So far so good, but we're trying to get at the acceleration. So in order to do that, we need to think about a net force equation. Our net force is equal to the force due to gravity on A plus force due to gravity on B. That's equal to the mass times acceleration of the system. Now, this mass, remember, we have to be careful about this one. This has to be our total mass. So for this thing, I'm going to just call this mass total, and then I'm going to kind of write another equation over here where mass total is equal to the mass of A plus the mass of B, and so that's going to be equal to 7.0 kilograms. There it is. All right, so we're trying to solve for acceleration. In order to do that, we're going to do the same rearrangement that we did above. Our acceleration is going to be equal to force of gravity on A plus force of gravity on B divided by our total mass. And so now we have to look at these and think, okay, well, these can't both be positive. One has to be positive, one has to be negative. I'm going to make this one my negative one just because that's how I roll. I like to put the one on that side negative. So we're going to have minus 50 newtons plus 20 newtons divided by our total mass, which was 7 kilograms. So we end up with minus 30 divided by 7. I think that's 4.5. No, it would be 4.5 if it was 8. It's supposed to be 8. Okay, 7. All right, so I got minus 4.29 meters per second squared. And so that's how much it's going to accelerate in the negative direction, which is going to be as A falls. So A is going to fall with an acceleration of minus 4.28 meters per second downward. B is also going to move at that same acceleration, but upward. So next it says, how long will it take for block A to fall 2 meters? So we got different information here. How long is the time? 2 meters is a displacement, right? A distance. And we know the acceleration. And so if we know those things, we're going to solve for time using this. This is back to our equations, guys. Right? We know that our initial velocity was 0, so that's something to keep in mind. That kind of lands us at this equation in the middle. The change in position is equal to 1/2 times the acceleration times the change in time squared, because our initial velocity is 0. So I'm going to rewrite that back over here. Our displacement is equal to 1/2 times the acceleration times time squared. So we're solving for the time. We'll just work our way through this. So I've got 2 meters, 2.0 meters equals 1/2 times minus 4.29 meters per second squared times the change in time squared. So I'm going to multiply both sides by 2 to deal with the 1/2. So now I've got 4 meters equals minus 4.29 meters per second squared times time squared. Then I'm going to multiply both sides, divide both sides by this minus 4.29. Get my handy calculator. 4 divided by my answer from the previous problem. So now I have minus 0.93 meters squared per, whoops, actually the meters go away, doesn't it? It's just 1 over second squared. Is that right? Nope, just second squared. Second squared equals time squared. So time is going to be the square root. Can we have a negative time? Does that work? That doesn't work. Here's what we did. If this is, if A is falling, A falls downward, and so this should be negative, which means this should be negative, which would give us a positive time over here. We can't have negative time. This is not a time machine problem. So if I'm going to do the square root of 0.93 seconds squared, what I will get, I got 0.97 seconds. So almost a second for it to fall 2 meters. Do you guys have any questions about number 4? All right, let's see if we can get this done in under 5 minutes. 2 lovers are parked 10 meters from the edge of a cliff. This is not safe, guys. In a car whose mass, including that of the occupants, is 1,000 kilograms. A jealous suitor ties a rope to the car's bumper and a 50-kilogram rock to the other end of the rope. He then lowers the rock over the edge of the cliff, and the car, which is in neutral, accelerates towards the edge. All right, so it says this is like a modified Atwood's machine where we've got a mass sitting up on a flat surface and a mass hanging over the side. So the first thing we need to do is draw force diagrams for the rock and for the car. So we're going to draw our car, fancy car as usual. And then there's a rope attached to it with a rock. And so our force diagrams are going to be that we've got gravity on the car, normal force on the car, and we've got some kind of pull, pulling it forward. And then we've got a rock, right? And the rock is experiencing gravity. And the rock is pulling up on the vehicle. And we know that because these are equal and opposite forces, right? This is a Newton's third law pair, that those two pulls are the same. So we know that. Okay, so there's our force diagram. Next, we have to determine the acceleration of the car towards the edge. Let's see. So we should start with a net force equation. So our net force is going to equal the pull on the car plus the pull on the rock. And these two are going to be equal and opposite each other, right? So when we add them together, they equal 0. Plus the force of gravity on the rock. And that's going to be equal to mass times acceleration. Okay, so in order to figure out the acceleration, what we need to focus on then is just this part. The tricky piece here is that we're going to use a different mass to figure out gravity than we use over here. So to figure out the mass, the force due to gravity on the rock, we're going to look at this 50 kilograms. So that's going to be minus 500 newtons. And that's going to be equal to the total mass, everything added up together. Our total mass is going to be the 50 kilogram rock and the 1,000 kilograms, the 1,000 kilograms in the car. And so when we solve this, we're going to have to use a 1,050 kilogram mass times our acceleration. All right, so we've got minus 500 divided by 1,050. I got minus 0.48 meters per second squared. That's much, much less than acceleration due to gravity because we have to accommodate the mass of the vehicle too. And so it's going to accelerate a lot slower. Lastly, how long, so we're looking for a time, do the people in the car have to apply the brakes before they go over the edge? So what we're trying to find is the time. We know that the acceleration is minus 48. So the acceleration is this 0.48 meters per second squared. We know the distance that they're going to travel is 10 meters. We know that their initial velocity is 0. So again, we're going to use that same equation. Our displacement is equal to 1/2 times acceleration times time squared plus initial velocity times time. Since our initial velocity is 0, we don't need to worry about that one. Then we end up with 10 meters equals 1/2 times. For our acceleration, I'm going to use acceleration in the positive direction and also use a positive displacement. So it's going to be 0.48 meters per second squared times time squared. And we're going to solve for time. First, multiply both sides by 2. 20 meters equals 0.48 meters per second squared times time squared. Time squared is going to be equal to my 20 meters divided by our 0.48. We get 42 seconds squared. And so so time is going to be the square root of 42 seconds squared, which is got 6.5 seconds. It's not a lot of time. Hopefully the brakes are good enough that they can offer enough force in the opposite direction that the car slows down. All right, and with that, we're at the end of our